Hi everyone, this is my first video on this channel, and in this channel I plan to cover topics ranging from Calc AB or Calc 1 to Calc BC, also known as Calc 2. And my main goal with these videos is just to help you guys out. So if you have any suggestions as to like a topic I should cover that you found especially confusing or difficult, just leave them below in the comments. Anyways, let's get started. So today we're going to be covering integrals, and the only real background experience you need to know for this are derivatives. So yeah, that's it. You don't really have to, even if you've never seen an integral in your life, this you'll understand this video. Okay, so let's talk about what is an integral. So an integral is, put simply, just the area underneath a curve. Okay, so let's say, for example, we have this function f of x, right? F of x, and we're trying to find this shaded area, so AS, right? So using integrals, so we can basically write this. So here's the notation, right? So you have this big S, this elongated S. So this is your integral sign. And then down here you put your lower bound, so A to B. And all this means is that you're taking the area between x equals A and x equals B, right? That's all this means. And then here you put your function that you're integrating. So f of x dx. So this, all this means, all this dx means is with respect to x, right? And yeah, I mean, it's not really necessary right now, but it will come really handy later when you get into U sub and more advanced concepts. But anyways, let's just start with this, right? So now we know the notation, but how do we actually go about evaluating integrals, right? And to do this, we're going to call upon our friend from before, derivatives. And it may seem weird because it seems like we're connecting two completely separate concepts, right? Because a derivative is the rate of change of a function, and an integral is the area underneath a function. And it's not immediately apparent how they could connect, but as you'll see very quickly, they are instrumental in understanding each other. All right, let's get started. So, first of all, to take a derivative, we need a function, right? And as it stands right now, this is a value. This is not a function. So let's vary this top bound. And instead of saying b, let's call it x, right? And here we have a problem because our function is in terms of x. So let's change that. Let's say our function is in terms of t, right? So f of t, and our upper bound is x. So now we have the area, let's say a of x, right, is the integral from little a to x of f of t with respect to t, right? And so I'm defining this as a function a of x because it'll make the notation later on simpler. So let's now take the derivative of a with respect to x, right? Let's see what happens. I mean, it could be interesting. So let's use our derivative notation, right? So we have, it would be, or first of all, you'd have the limit as dx approaches 0 of a of x plus dx minus a of x all over dx, right? So the question is, how do we figure out what a of x plus dx is? So let's call this whole area, let's call it S, right? So this is the shaded area, okay? So a of x is simply s because it's the integral from a to x, right? A to x. Now we need to figure out what a of x plus dx is. So let's say we add some very, very tiny amount dx, right? So this is our dx. And when you have such a small dx, you can approximate this area as a rectangle, okay? So we have this area that we're adding. Now let's find the area of this rectangle, okay? The height, as you'll see, is just f of x. And the width is dx. So the area of the rectangle ends up being dx f of x, right? So let's rewrite this. dA dx is equal to a of x plus dx is simply the area from a to x plus dx, right? So this is s plus this rectangle. So s plus, and we found the area of the rectangle to be this. So s plus dx f of x minus a of x, which is simply s, right? Divided by dx. And once again, we're taking the limit as dx approaches 0. So s plus s and minus s, these cancel out. Now we're left with the limit as dx approaches 0 of dx f of x over dx, which is simply f of x. Now this is remarkable, okay? We took the derivative of the area function. So the derivative with respect to x of the integral from a to x of f of t dt, right? Because this is what we define the area function as, is equal to f of x. So in other words, if you have a function and you take the integral and then you take the derivative, it just gives you the original function. This is basically just saying that the derivative and the integral are inverse operations. It's just like multiplication and subtraction, or I'm sorry, addition and subtraction, or say multiplication and division. These are simply inverses of each other. They undo each other. So this is the first part of the fundamental theorem of calculus. Okay? Now let's move on to the second part. What do we know from this? We know that, let's rewrite this, the derivative of the integral from a to x of f of t dt is equal to f of x, right? Now, let's undo this derivative, right? So we're taking the antiderivative of both sides. So you're left with the integral from a to x of f of t dt is equal to, let's call this big F of, so big F of x is the antiderivative of little f of x. And this is just convention, right? So big F of x. And notice here we have to add a constant term because no matter what this constant is, when you take the derivative of both sides, this constant is going to go away. So theoretically, you could have any constant here, okay? Now, we have big F of x plus c. But what is c? To figure that out, we can use a clever trick, right? Let's substitute x equals a. So if we substitute x equals a, we get the integral from a to a of f of t dt. Now remember what an integral is. It's the area under a curve, right? And essentially this is saying if you take the area from a to a, what do you get? And the answer is 0 because you haven't actually moved anything, right? There's no area here. So let's plug that in. This is 0 is equal to, and we plugged in x equals a, remember. So you get f of a plus c, which means c is equal to negative a. Now if we plug this back in, the integral from a to x of f of t dt is equal to big F of x minus big F of a. This is the second part of the fundamental theorem of calculus. And that's where I'll end this video. In the next video, we'll talk about actually evaluating these integrals using common methods like reverse power rule, U substitution, etc. Um, Thanks for tuning in, and I'll see you next time.